Okay, so this is a question about particle physics. So we'll go through this one fairly quickly. So name one process in which a proton changes into a neutron. Well, that is beta decay. We'll figure out which one it is. So a proton changing into a neutron. Okay, so to balance this, or to make this viable, firstly, at the minute, charge is not conserved because we've got +1 on the left, we've got 0 on the right, and the particle which comes out of this is a beta plus particle. We're still not quite done because we've got a lepton number of -1 on the right-hand side and a 0 on the left, so we need a normal electron neutrino. Okay, now it's not actually asked us for that thing. We just have to name it, and we would name it as beta plus decay. Okay, another one that you could have here is electron capture, because we know that what can happen also, I'll draw it up here, we can also have a proton grabbing an electron from the inner shell of the atom, and the proton turns into a neutron, the electron turns into an electron neutrino, and that gets shot off. So this is called electron capture. Okay, I won't dwell on this, but this is one of those processes which people forget about. It's super important. You need to know the differences and similarities between these two processes. Okay, so if you were doing an experiment in a lab, you need to be able to explain how you would tell the difference between electron capture and beta plus decay. They both turn protons into neutrons, but what comes out is different. All right, so name the particle interaction involved in this process. This is, of course, the weak interaction. And we know that because it involves leptons. And and the weak interaction is how leptons can change quarks into other things. Okay, write down an equation for the process you stated in part A and show that the baryon number and lepton number are conserved. Okay, so we've already written down the equation. That's here. Let's bring it down. Okay, how do we demonstrate baryon number? So baryon number, it's very simple. All you have to do is you just write down numbers where they correspond to each thing. So proton is +1, neutron is +1, beta plus is 0, and the and the normal electron neutrino is also 0. This is sufficient. That's all you have to do. You write down the equation in that way. Lepton number, similarly, get the right number. So lepton number, proton lepton number is 0. Neutron lepton number is 0. Beta plus is an antiparticle. Remember, it is an anti-electron. So this is -1. And the electron neutrino has +1. So we've got 0 is equal to 0, -1 plus 1, which again, is fine. What's happened here? There we go. Okay, good. All right. Quark composition of a K+. Okay, so K+ is a strange meson. Strange meson. So we need a quark-antiquark pair. It must contain a strange quark. Now, if you look at your data sheet, you will find that the charge of a strange quark is -1/3. It's the same as a down. So to get a K+, we need an up quark, which is +2/3. We need an up quark and an anti-strange. Okay, an anti-strange is going to have +1/3 charge. So those two together will get you your K+ charge. Okay, beautiful. A K+ charge, K+ kaon decays into a pi plus and a pi minus. Explain one property which is conserved and one property which is not conserved in this decay. So let's go back to pink. Oh, look at all these. Let's try that one. So let's write it down first. K+ goes to pi plus pi naught. So the thing that's conserved, obviously, is charge. We've got +1 charge, and we've got +1 and +0, so that's fine. So this is for charge. Now, the one thing that's not conserved is strangeness. Now, K+, we've got a strangeness down here. Now, if you remember, the strange quark has a strangeness of -1, and that's a quirk of how it was discovered. So a normal strange quark, not the anti-version. So the normal strange quark has a strangeness of -1. So on the left-hand side here, because we've got an anti-strange, we've got strangeness of +1, and we've got 0 and 0, because these are both pions, and pions are not strange. So not conserved here is strangeness, and I think everybody got that. Okay, that's it for question 2. Let's pause there and start again in the next one.